So, welcome to my dear students and learners. So, today we are going to discuss the this is a analytical method by mathematical calculation how you can estimate the velocity distribution inside a fuel subassembly. Uh, Today there are lot of packages are available through which by simulation you can estimate it, but once you are going for any simulation, first it is to be benchmarked with some small experimental setup. So the same thing I did few years back with few of my training school students. So that only just I am going to share with you today. Some of my students uh, asked me, so I remembered that, and that only I am going to share. So if you take the cross section of a fuel subassembly, so you can see here. So these are the fuel pins, okay, and it is arranged in this fashion, and there will be uh, spiral wire spacers will be there. So this is the cross section, okay, this is the plan view. So if you see this particular, it's a hexagonal shape. Normally the fuel sub assembly will be hexagonal shape, and inside there will be lot of fuel pins, okay. So through the gap of this fuel pin inside a sub assembly, the coolant will flow, okay. So we are going to basically estimate that velocity distribution. So now if you see the geometry here, broadly three types of flow area or flow aperture or the fluid flow area is seen. So one is this, you see, this is the type 1 interior channel, another is type 2 edge channel, and another is type 3 corner channels. So basically for a hexagonal fuel subassembly, there will be three types of channels whose areas are identical. So basically we are going to estimate that. So these are the, it is purely, we did one experiment. We took one pipe, hexagonal shape one pipe taken like this, okay. So here inside there will be, we kept some um, solid tubes like this. These are the solid tubes, and here we injected, this experiment we did with water. So we injected the liquid, and here we measured the velocity, the pressure loss, the pressure drop, all these things we measured, and with that value we validated, okay. So these formulas are available in standard fluid dynamics book, uh, because during my college days I studied my fluid mechanics, the book, I think RK Bansal, that is the standard book, okay. So from the Bernoulli's equation, the pressure drop, so here I is the ith channel, so the I value will be 1, 2 and 3 for this particular case, okay. this Fi is the friction loss or friction factor, and L is the length. This length is L, okay, and this Di is the effective diameter. DEI means this is the effective flow diameter or flow aperture for ith channel, okay, and rho is the density of the liquid, and this Vi is the um, uh, velocity. This is the velocity in ith channel, okay. So this basically equating the um, uh, dynamic head and the static head, simple Bernoulli's equation, okay. Now if you consider the mass flow rate, the total mass flow rate, okay, is the mass flow rate, that is equal to this rho into the total area. The total area means for all the three channels, the total area into some average velocity that is measured here, from here is the average velocity, okay. Now for all the three channels you can rewrite this, because the value of, as I told, the value of I, it will be, there are, in the previous slide you have seen there are three types of channel: type 1, type 2 and type 3. So we are going to estimate the velocity for each channel, means through this area what should be the liquid velocity, through this area what should be the liquid velocity, through this area what should be the coolant velocity, that we are going to estimate. So you can write simply, it will appear as this, okay. Now this is the equation, it is, you can, this is the Laplace relation for frictional factor in liquid flow, okay. This mu is the dynamic viscosity of the liquid, okay, and the C and M, these are some constant, okay. So we created turbulent flow, and as per the Laplace relation for friction factor, if there is a turbulence, if you consider turbulence, uh, there is a turbulence, there is a turbulent flow inside a smooth tube, then this value is 0.25, normally it is, anyway that is different. So now if we put this value, if I substitute this in this equation, so this equation, it will turn to this, okay, correct. Now from here you can find out this V2, this relation, you can find out V2 and V3 in terms of V1, correct. So your V2 is equal to, say if you want to find out V2, your V2 is equal to this term divided by this term into this term, okay. Similarly V3 also, V3 is equal to, so V3 is equal to this term divided by this term whole to the power 1 by 2 minus n. Similarly V2 is equal to this term by this term uh, into this term whole to the power by into V1, okay, whatever may be, because this term is common, okay, power is same for the top. Now we considered that entire flow through the subassembly is incompressible. So based on your uh, fuel subassembly design, this number of channel, it will vary, okay. So you consider in general formula. So this is the number of type 1 channel, number of type 2 channel, number of type 3 channel, okay, and this is the effective area for type 1 channel, type 2 channel and type 3 channel, okay, and this AT is the flow area, total flow area for all the channels, okay, that can be calculated. And this V bar, it is the average axial velocity. So we measured it from here, as I told you. Here we measured that velocity, okay, using some flow meter. Now, from the previous slide, we obtained the V2 and V3 value in terms of V1, correct? So that if you substitute in that equation, so this equation will turn into this. Now there everything is in terms of V1, then your V1 is equal to this divided by total this term, okay. Now if you write in short form, it will be like this. So this way you can calculate the V2 and V3 also. With that we can find out. So as I told, we exact that figures, how much velocity and all, I can't remember, but we considered it as turbulent, considered for turbulent flow in smooth tube. So we took the value of m as 0.25. With that we validated, and our COMSOL model also benchmarked with that small experiment. So I hope the velocity distribution inside a fuel subassembly is now clear, and this is the analytical way to estimate it. Thank you so much. Thanks for your patience.